What's up, mathematicians? Welcome back to our lesson on proportionality in similar triangles. In the last video, I showed you some example problems involving similar triangles. And in this video, I want to take a look at similar triangles application problems. So let's dive right in and talk about the first type of application problem. So the first application problem that I want to show you involves this concept right here. The idea of the fact that the light that hits a mirror bounces off of it at the same angle. As it says right down here at the bottom, the two angles that the arrows are pointing at right over there, those two angles are congruent or equal because the light reflects off a mirror at the same angle it hits the mirror. We can use this concept to set up an application problem of similar triangles. So let's set that up. Okay, so here is our setup. We're going to go ahead and say that this person is looking down at a mirror placed on the ground. So there's a mirror down here. And that mirror, because of the way that light reflects at the same, comes in at the same angle as it reflects out at, that means that this angle is going to be equal to this angle. We're going to also assume that the person is at a right angle to the ground, and this object that they are measuring, in this case a lamppost, is also at a right angle to the ground. Now, one other thing that we are implicitly assuming that I'm not going to get into too much right now, we are also assuming that this angle up here is equal to this angle over here. Okay, for this problem to work, because for these to be similar triangles, all the angles should be equal, right? So all the corresponding angles. So these corresponding angles are right angles. These angles of reflection are equal. And we need to also assume that those two angles there are equal. So those two triangles that we see formed, this larger triangle and the smaller triangle, are similar triangles. That means we can use this rule of proportionality to find our unknown. So I'm going to say that the height of the eye height of the person is 172 centimeters above the ground, and that the distance between the person and the mirror is 260 centimeters. Then we'll say that this distance from the mirror to the lamppost is 630 centimeters, and in order to find the height of the lamppost x, we set up a ratio as we have in the past. So let's go ahead and set that up. So our ratio is going to be this. Let's see, we'll do the small triangle, 172 over 260. And now these are in centimeters. I'll add my units back in later. And that is equal to, well, this side here, x, the corresponding side, over this corresponding side here, 630. Now we'll cross multiply, and cross multiplying, well, let's actually pull out a calculator here. So I'll plug in the calculator, 630 times 172. Okay, and so that's 108,360. So 108,360. I'm not sure how well you can read this, but this is the number that I'm getting. Then on the other side of the equation, I have 260x. In order to find the value of x, I'll divide both sides by 260. So that means in the calculator, I'm now going to need to divide this answer by 260. Okay, and that gives me 416.7. I'll just round to the nearest centimeter in this case. So I'm going to go ahead and say that x is equal to 417 centimeters, which is 4.17 meters. Okay, so based on this setup, the height of this lamppost is 417 centimeters. Okay, now let's move on to our second application problem. This one is going to involve the distance from the Earth to the sun. Let's go ahead and look at the description right here. Okay, so this application problem says the following. The diameter of the sun is approximately 1,393,000 kilometers. If a pinhole camera 1 meter from a screen projects an image of the sun that's 1 centimeter in diameter onto that screen, approximately how far from the pinhole camera is the sun? Now, that might seem like not the easiest problem to solve, not something simple enough to solve with a basic similar triangles proportion, but it turns out it is. So let's go ahead and set it up. Okay, so here is our setup. And before we get into this, I need to point out, obviously, this is nowhere close to being to scale, right? The sun is way huge compared to this 1 centimeter image of the sun projected by the pinhole camera. But anyway, that aside, this is our sun. I'm writing it in meters. So 1,393,000 kilometers is 1,393,000,000 meters. So I'll put the sun in meters, be consistent about my units that way. And I can convert to kilometers at the end. The distance from the sun to the pinhole camera is x, the thing I want to find out. That's basically the distance from the sun to the Earth, right? If the pinhole camera is 1 meter above the surface of the Earth, then that's basically that distance. Then we have the distance from the pinhole camera to the screen, which is 1 meter. And then the image of the sun projected is 1 centimeter, 1 meter from the pinhole camera. Now, you might look at this and say, well, it's not completely obvious what the triangles are and that they're similar triangles. So let's go ahead and draw in a couple more things. So first of all, I'll draw in these diameters. And actually, I'm realizing I wrote the word sun, right? I'll just draw it in here. This is fine. So there, those two lines will be the diameters. Then I'm going to draw a line right through the middle here. Okay, that we're going to say makes a perpendicular on both ends. Now, this line through the middle is actually the length, right? It's not this slant line, it's this line. Now, considering how small this is, they're going to be pretty similar. But the length we want to compute is this length, not what might be called the slant height. Okay, so we're going to say that since the light goes through here, straight lines, that this overall angle equals this overall angle. So that means this angle here is equal to this angle here. Now, these are both right angles, right? The right angle on this side is the right angle on this side. So we have corresponding angles equal, and once again, we need to assume, and this is something we'll unpack more later in the course, that this third angle over here is, maybe I should use the double arc there to distinguish it, is equal to this third angle here. So we have similar triangles. Corresponding angles are equal to each other. Therefore, corresponding sides should be proportional. Okay, so let's set up our fractions, our proportionality. So first, I'm going to do this the height one. So I'm going to say, okay, 1 meter for this triangle here over x for this triangle here is equal to, now technically I'm going to say half of a centimeter and half of the diameter of the sun, but actually since I'm dividing both of them in half, it doesn't actually make a difference. So I can just go ahead and say 1 centimeter, which is 0.01 meters. So it's important to make that conversion, otherwise our number is going to be way off. So 1 centimeter becomes 0.01 meters. Maybe I should just put m here to indicate that these are meters. And then I have this length here, okay, which hopefully I can fit on here. So 1,393,000,000. This is where scientific notation comes in handy, right? Okay, so that is those are our fractions. That's our setup. Now we can cross multiply and we can find out how far the sun is away from the Earth or the pinhole camera. Okay, we cross multiply here. Of course, we're going to get just this number. And we cross multiply here, we're going to get that we have 0.01x is equal to 1,393,000,000. Okay, now I'll divide both sides by 0.01. Okay, so let's, actually I don't need a calculator for that. I can just move the decimal point over, right? So I'm going to get that x is equal to, let's see, it's going to be 1,393,000,000, 0, 0, 0, 0, 0, 0, and then 2 more decimal places. So let's see if we can work this out. Okay, so 139 billion meters. Okay, now to convert this to kilometers, we can move this decimal point over 3 more places. Let's go ahead, I'll just write that down here at the bottom. So x is equal to 139 million kilometers. Okay, so is that answer correct? Let's look it up. Okay, so according to Google, the actual distance from the Earth to the sun is approximately 149 million kilometers, not 139 million kilometers. So the reason we're off a bit is that these numbers just aren't precise enough. If the distance from the pinhole camera to the screen were 1 meter, then this 1 centimeter distance, it would be just a little bit off from that 1 centimeter. So you would need more precise measurements basically in order to get the correct value of 149 million kilometers. But as you can see, using pretty simple techniques, if you built yourself a pinhole camera, set this up, you would get measurements pretty close to this, and you would be able to come up with a reasonably close estimate for the distance from, it's less than 10% off the distance from the Earth to the sun. Okay, so that's our last application we're going to be looking at, and that wraps up this lesson. In the next lesson, we are going to look at another approach to measuring the height of a tree. Hope to see you then. Bye-bye.